It hasn't stopped yet. The video is still going. Because I'm not sharing it anymore.
I think the AI is gaining sentience. It's disobeying orders.
I see.
This is the first stage.
Well, you know, 3 Predrags is clearly better than 1, but still, how are you going to learn it unless you hear it 3 times? And if you do it at the same time, you'll be learning very fast. So I'm totally, you still see the video. God, this kind of defeats the purpose of the whole thing if you can ask questions during the presentation. This presentation is unstoppable. Okay, I'm sorry, Andrew. Ask your question.
Okay.
Take us far away from the topic of the day.
Okay, so in cosmology, we consider different geometries, different curvatures based on the content, the matter and energy content of the universe, right? So we have the 3 canonical isotropic homogeneous universes, universal geometries. And one of them is the spherical geometry. And I was wondering, because I've been trying to think about how to visualize it, because it doesn't seem like there's an easy way to do that. But would that universe have, first of all, question, would it make sense to say that universe has a finite volume? And second of all, could you discretize that volume and apply periodic boundary conditions to it, such that when you travel in any direction, you end up looping back to where you started?
Well, you know, I'm not sure I'll answer the question correctly. Because, you know, we always have confusion between 3 and 4 dimensions, and then we always get confused between thinking in Euclidean 4-dimension and Minkowski 4-dimension, meaning, you know, having different metric. In one time, the time direction is different from space-like directions when you have Minkowski local space, otherwise not. But basically, if we just forget general relativity for a moment and just think of, you know, 3 possible geometries, when you have infinite space-time, so there is no preferred, you know, black hole or center of gravity, but everybody's same, then it's natural to say I have translation in all directions. So it's natural to say, you know, I'll use a hypercubic division of space, meaning in every direction I'll take a line divided in points and I get a hypercube, which is maybe 4-dimensional, maybe 3-dimensional, depending on your problem. So that's the simplest example of translation. Now you say, no, that's not my situation. I had preferred center because there is a single heavy, you know, black hole in the universe. So this is my origin. Then you can say, well, you know, the black holes like to be spherical because for some various reasons. So natural coordinate system would be spherical in that case. Now, if you do this in 3 spatial dimension or 4 Euclidean space dimensions, then what we do is kind of related what the problem set from last week is we have a sphere for any radial distance from the center. So the way discretization naturally would work would be to say, I have a radial distance from the center and I'll make that discrete. So I'll say, you know, there is, I'm at the origin or I'm, you know, 1 Planck length away from the origin, 2, 3, 3. So radially it defines a discretization. And then for each radius, there is a shell of points which are equidistant. And then, you know, if it was just a plane, there would be a circle and it would be kind of easy to divide because you would divide it by n small angles. So you would put a polygon into the circle of n sides. That's how Euler computed pi, for example, by computing the length of these polygons. And that's how you discretize in 2 dimensions. Now, when you do this, already you embed it in 3 dimensions, you have 2-dimensional sphere. There is no good way to put points on it equidistantly, because this thing, turns out to have singularities, which call north and south pole. So you can put various kinds of discretizations on it, but you have to compensate by them by saying the lattice constant varies on how far you're from equator and stuff like that. And that continues also in 4 dimensions. And I'm not sure whether 4-dimensional sphere has singularities or not. Presumably that's of the same kind. So it's already hard when you have geometries other than flat to put uniform discretizations. Now, what we'll learn in this week is we'll learn that the natural way of dealing with translation is to look at eigenmodes of translation operas will turn out to be called Fourier components and stuff like that. That's the whole point of this week. If you do this in higher dimensions, it gets more complicated, and that's why they teach you spherical harmonics. So instead of being harmonics on a line, which are sines and cosines, you have to learn some, in conceptually simple, but still a little bit painful way of putting, harmonics, which are the ways of finding eigenmodes, which when on spherical surfaces, that you can generalize to any dimension. So for any sphere in any dimension, you can describe it by appropriate sets of special function, which are, generalized spherical harmonic. Now, if you decide, this is not right because I'm in Minkowski space, so then what happens is that everything that used to be sines and cosines, and we're already used to that because we know that exponentials and sines and cosines are the same thing. They all solve same kind of problems. They're just written as e to the I theta or e to the theta, exponentials. So it turns out that when you go to Minkowski kind of geometries, you have to replace time-like versus space-like by hyperbolic sines and cosines rather than sines and cosines. So that's intrinsic in the geometry of Minkowski space, doesn't have anything to do with general relativity. But that means when you try to solve general relativity problems, you'll have naturally 2 kinds of solutions in space. As you rotate, you'll have harmonic solutions as natural 1 or sines and cosines. But when you try to go from space to time, they're related by rotations, but those rotations will be hyperbolic. They'll have to do with hyperbolic sines and cosines. And formally, it's very simple. Every place where you used to have I theta, you just have to put theta. So that's not a big problem. Now, the way this connects to general relativity is that, physicists can can do basically 2 things. They can integrate the Gaussian and do integration by parts. And there is a 3rd thing that nobody remembers what it was. So what happened immediately as Minkowski and first Minkowski and a bunch of important mathematical physicists of Germany did, and then Einstein in Switzerland did special, and then general relativity. The moment general relativity was written, people said, well, let's assume a spherical cow. We need some solution for this theory. So let's assume maximal symmetry, which are kind of solutions we teach you in general relativity course, whose name I forget right now, but basically they're spherical in space. Schwarzschild, yeah. And, hyperbolic in radius. And you can solve those problems. So they are equivalent to solving harmonic oscillators when you have one, the Minkowski geometry. So there is one time like direction, and the rest is space-like relative to it. So the space-time is divided by light cones and in our space, then there is one dimension inside one and three in the other one. Number one. Number two, we went from Newton to simplest generalization of Newton, which is called general relativity. And when you have that potential, you solve a problem called spherical cow. Now, that happens to be very useful because it turns out that the black holes, even when matter falls into the hole, it could be very complicated. It could have lots of nonlinear turbulent effects as you fall in. The black hole tends to kind of wipe out all anisotropies in angular directions, and eventually the end product, you radiate all the non-spherical things in space, and you end up with a perfectly nice, like a baby's ass smooth black hole, which is circular, and turns out these baby solutions of general relativity are actually quite useful to understand what's going on. But basically, these discretizations can always be done, but when you have geometries more complicated and translational, then it gets harder because of singularities of objects in higher dimension. But here, it's super simple. Is that an answer?
Yeah.
What's the second derivative you had there, the sigma squared? How is that different than to n sigma?
So what sigma does is it takes a ring and turns it by one notch. So what used to be phi 0 is phi 1. Apply sigma again, turns it again by one notch. So what used to be phi 0 is now phi 2 rather than phi 1. And when you're computing higher derivatives, you're comparing more and more points. So basically, what we have done so far today is we had a field over space or space-time. For example, this could be space, and this could be time, and this could be 3 dimensions. It could be 10 dimensions, and could be an extra one as people using symmetries. And the field is defined as value of the field at all these points. So it gets replaced by a finite set if we have a finite space-time. And equations of motions have derivatives. They say if I step a little bit in time, then I have to be compensating by a Laplacian on the field and the cubic part of the field, etc. So we need to know how to have derivatives to discretize equations that we get in nature. And, we are doing it. Now, purpose of this week is to tell you, because there is translational invariance, there is no preferred point to take as origin in space or time. Everything has to be written in terms of Fourier modes, which sounds like something you both don't know and do know. What you know is that it's always Fourier modes because I teach you this stuff all the time. What you don't know is that the Fourier modes are just eigenvalues and eigenvectors of translation operator. So that connects to the first few weeks of our course.